Hi everyone, I'm Amanda. I built a predictive model to diagnose anemia based on blood count data. This dataset is from Kaggle.com. It is called Anemia Types Classification. It contains 14 different features of various blood testing metrics and 9 different classes as the target variable, one of which is healthy, and then 8 different subtypes of anemia. So my project is actually a pipeline. I chose a less intensive data set that didn't need a lot of pre-processing because I really wanted to focus on building a solid pipeline in R, which we haven't got to do yet. And I also wanted to do my project in Python to practice my, my coding skills in other languages. So this project ended up being a mix of Python, R, and SQL, mostly Python. So if we open this README, we can just, it just gives like instructions of how to conduct the pipeline, like make sure that all the files are in the folder, make sure you have the packages installed. And this also just requires Python to be available to RStudio, and everything else that it will need to access in Python, all the libraries will be installed within the virtual environment in this project folder. So we definitely need to open the final project. That will ensure that we're in the directory, and from there we can knit our file. While this is knitting, I'll just take a second and explain a little bit more about the pipeline. So it was pretty difficult to get this virtual environment to establish and make sure that anything installed stays within the folder so that a peer reviewer can delete it after they're done. But any packages that are installed either through R or Python are universal, so they can be used by any data file in the project as long as you're in this project folder and in the project. And then I download my data from my personal GitHub. It's a URL, and then I create a SQL database. And I upload the data to the SQL database and render the data prep. So the other part of the pipeline is the data prep. I didn't do it in the main folder where I make all of my models. I have it in a separate folder that also knits. It's also viewable. You can see what it does and read it like a markdown journal. But I wanted to keep it separate from my model building because it's just like been really hard to have everything in one file in this class with messy data sets. And this isn't a messy data set, but the purpose of choosing a cleaner data set was so that I could like focus on this type of process and learning how to do this. And I think this will really benefit me in the future. Okay, my file just finished knitting. I just wanted to go over the visualization a little bit. I separated the blood cell counts by their classes, so whatever diagnosis or healthy, and visualize each feature based on those separations by classes. I wanted, one of my models is random forest, so I feel like I could get good insight of like what might be our primary predictor in this case. It's also really interesting to note, so this is actually the data already cleaned, and the reason it's already cleaned is because these blood counts binned so horribly with all the outliers. So this is an outlier from way over there, and it forced everything else into one bin. So that's for healthy people. So it's like impossible to gain any insight from this. So I removed all the extreme outliers before visualizing and just kind of tried to gain insight. There's nothing like that screams it would be a principal predictor. I think hemoglobin kind of shows a little bit of spread in the disease types. MCV platelets also showed a little bit of a difference, so those might be primary predictors for our models. Other than that, it's just really subtle little things that the machine algorithms are a lot better at predicting and being able to differentiate than our human eye. I also, showed the class distribution. So you can see that the two most popular classes are like almost half of our data set. And then we have over half of the target features or target classes are represented by like less than 5% of the data. So they're really, really rare. I'll do a little quick code demo from my data prep file. So this is the one where I showed before that it is rendered by the main file. So that just knits this file automatically. And then the data gets uploaded to a SQL database. So like I said before, my data set was really clean and a good learning data set for practicing Python and making a pipeline, but I did not actually use this hyper clean data to build my models. It wasn't necessary. I found that my models relied on hyperparameter tuning, not data cleaning for this particular data set. So cleaning the data didn't make a difference in performance. And just for the sake of not tampering with patient data, as I would want to avoid in the real world, I just used the raw data. But I did go through multiple just cleaning steps just for demonstrative purposes, and of course remove those outliers for visualization. So we can see we evaluate for missing values here, and then I imputed, or I removed some values and I displayed them here. And then I imputed them using the median, and I organically found the missing values again instead of using, you know, the pre-known indices, just to demonstrate that I could do that. Then our outliers, and this is all in Python also. I know it might be hard to tell from the video, but it is all in Python. Outliers displayed their values and then what they are replaced with. And then our distribution and the correlation matrix. This is a really nice mechanism in Python. I think it's a little cleaner than ours correlation mechanism because the data frame package has this correlation function built into it. So that's really nice. And then finally, we save the clean data set to our SQL database just for the sake of visualization, like I said before. And to show that we could, if we want to use this kind of pipeline on a different data set that really required cleaning for modeling. Okay, so the models that I chose for this project were random forest, support vector classifier, and neural network. The reason I chose these, random forest, it's obvious, it's interpretable, so oftentimes an interpretable model is legally required for healthcare data exploration like this. They also all accept the same shape of data, and I wanted to really, hit the Python practice hard, so I just went with the same shape of data for all models, which is really nice. And also, they're used in healthcare a lot for models like this because blood testing data is already standardized. Just the nature of how it's read by the machine and the results that are produced from it, they're already standardized. So these models work really well. They pretty much require standardized data on it like this, and blood testing data is just already standardized. So these were really good models to use for this data set. And I will jump over to my code and I'll show you a little demonstration. I'll do SVC because it takes the least amount of time to run. So I constructed each of my workflows like this for model building, where I got a base score of the model, I tuned hyperparameters, I adjusted hyperparameters, the hyperparameters were tuned in a loop with bagging. I chose F1 score as a metric for them, so it just goes through each hyperparameter and it chooses the best combination. It saves the maximum average F1 of the cross-validation produced models. So I did this. Oh, right, and I should mention that my data was partitioned using stratified sampling since I have such small minority classes in my data set. So this ensured that every model in the training phase saw every single class, and in the testing phase was tested on every single class. So we can make our SVC model. It has already a great F1 score, but we can tune it even further with hyperparameter tuning. And I have a great computer, so it happened really quickly. And then we can evaluate the final model. So We have a C-value of 100, a gamma of 1, and a kernel of linear. I think that is almost, yeah, so the C-value is the default. The gamma is a little different, and it used a different kernel. So great, and it produced a slightly better, it's actually a bit better. It's a bit better. So like 0.91 F1 versus 0.82, which is great. That's a great performance gain from hyperparameter tuning. And this is our classification report. Shows everything. It shows that these underrepresented classes are suffering a little bit in performance, but I think that's just the nature of it. I'll just touch for a second on the metrics of my other models. They went through the exact same process of tuning, and the random forest has an F1 score of 0.98, which is outstanding. Its accuracy is reported above here, 0.98 also, so really outstanding model for this data set. Neural network was a little bit different, and I did have to encode the target variable. Neural network cannot handle anything but numeric data, so even the target variable has to be encoded. So Python offers a really nice package for doing that. You can see it started at 0.9, and after hyperparameter tuning, it is still 0.9. It's not much better. Oh well, that's how it is sometimes. So let's look at the heterogeneous ensemble. The way I did this is I basically did like adding the F1 scores in a sense, where the primary model with the best F1 score is assigned, and that is usually used for all the predictions unless the secondary and tertiary model agree, in which case their F1 scores would have a greater weight than the primary F1 score. So no matter what, if they agree, then their prediction is used, else the primary model is used if they don't agree. I just wanted to print the classifiers, or the model order, so you could just kind of have a demonstration. So in this case, the random forest had the highest F1 value because that's our primary model, and the SVC had the second highest, and it really doesn't matter the order of the tertiary and secondary models because they're treated the same no matter what. And our ensemble has an accuracy of 0.95, and the F1 score is carried down here. This is my little table of the values, and it looks like it does not perform quite as well as the random forest, but that's to be expected because if the support vector classifier and the artificial neural network, or whichever are the secondary and tertiary models, have the same weakness, then by doing that additive effect of the F1 scores, they're going to multiply each other's weaknesses. So it's not surprising that the model performance suffered a little, but it's still better. The random forest is helping them out a little bit. I really learned a lot from this project. First and foremost, the capabilities of RStudio as an IDE. It can really smoothly integrate multiple different languages into its workflow, and it can establish a pipeline pretty efficiently. So I was impressed by that. I got to learn Python and machine learning. Scikit-learn is a really powerful package. It has a lot of great functions built in that can just make a really smooth model building workflow. I was really happy with the workflow I was able to come up with just from reading documentation and watching YouTube videos. So thanks Dr. S for letting us explore a little bit. Also just being able to talk to Dr. S about the virtual environment and just different intricacies of the pipeline was really helpful, that I just hadn't ever thought of or explored before. Yeah, so I was pretty happy with this project, and I'm excited to experiment with more data in the future. So thank you guys for listening.